Today we are looking at net ionic equations. Do y'all remember these wonderful, fun things that you had to first write the total molecular equation, then figure out what state it was in, and then split them up, and then cancel out things to get to the net ionic? So things haven't changed all that much. I am going to teach you a shortcut in a few days, but in order to do the shortcut, we really need to relearn how to do it the long way, because the long way is really chemically what's happening. And all a net ionic equation is kind of like the Cliff Notes. It's listing the only things that are changing in our final equation. So we have to apply the solubility rules that we did yesterday. So I'm going to do this first one, and we'll talk about it. Anytime you write down a substance, you have to write down whether or not it's a salt that's aqueous in water. If it is, what do we write next to it? AQ. If it's not aqueous, it would be solid. Anything else is going to be common sense, like H2O. What are you going to write next to H2O? Liquid. What would you write next to CO2? Okay, so that kind of thing you can figure out if it's not a salt that you're applying solubility rules to, because all of these are in an aqueous solution. So all we're going to do is we're going to start and we're going to write out the reactants. Potassium chloride, is that a soluble or insoluble salt? That is soluble, so we're going to put little parentheses here and write aqueous. And we're going to add that with lead 2 nitrate. So it's a lead with 2 nitrates on it. And is that soluble or insoluble? Soluble, because what rule? Big Daddy rule says all nitrates are soluble, so this is also aqueous. Another part of doing this is your ability to do a double replacement reaction. And we can do these with single replacement and things, but today we're looking at double replacement. And with double replacement, you just flip your partners. And so what is one potential product? Okay, what? Potassium nitrate. And is that aqueous or not? Yes, it's aqueous. Plus, and what is my other product? Lead 2 chloride. In double replacement reactions, oxidation states do not change, so it is lead 2 chloride. And we write that as, is that soluble? No, why not? What rule? The halogens, Hal hugs Aggies pretty badly. So they're all soluble except for one of these three. So we write solid next to it. Now the next job is we have to balance this equation. So how do we balance it? 2 KCl and 2 KNO3s. And we have 2 chlorines, 1 lead, 1 lead. All right, the next step. Anytime we have something that is aqueous, we're going to split it up into ions. So what we're doing now is we're going to make anything that can be ions, ions, and anything that's not ions is going to stay the same. So when we do this, we have to apply the 2. So it has to be 2K plus aqueous plus 2Cl minus. That 2, do you see how it applies to both of those species? Doesn't apply to just one because we have 2 KCl, so it's 2K pluses and 2 Cl minuses. Also notice that these have charges. If they don't have charges, you're getting it wrong because we don't have changes in oxidation states. When you put KCl in water, it doesn't make potassium and chlorine. It makes potassium ions and chlorine gases. That's one of my big pet peeves when we watch House or some medical show and they're like, give him some potassium, he's got, for electrolytes. You're not giving him potassium. He'd explode if you gave him potassium. It's potassium ions in solution, okay? So they lie on TV. So let's split this lead 2 nitrate up since it's aqueous. How would we split it up? A lead plus 2, and then what? NO3 2? No, we do 2 NO3s, 2 separate NO3s. When these ionic compounds split up, the ions are separated. So we have 2 nitrates. All right, so in our products, we have 2K pluses because we know that's totally ionic, soluble, and 2 NO3s, minuses. And then what do we do with that lead 2 chloride? Leave it alone because it is solid. All right, we're going to cross things out that are the exact same on both sides. And by exact, I mean exact number of things, exact symbols, exact charges. Everything about them has to be identical. If they're not, maybe you balanced wrong, so you need to check that. But if it's something you're going to cancel out, it has to be exactly the same. What did we call that stuff, those things we cancel out? Spectator ions, good. And that's legitimately what they're doing. From the beginning, spectator ions just literally float around in solution. They're like, yeah, what's up, and don't do anything. So what are our spectator ions? The potassiums go, and our nitrates go. So our final net ionic equation is what's left. 2Cl minus aqueous plus Pb plus 2 aqueous gives us PbCl2 solid. So the only thing that's ever in the net ionic equation is going to be what the components of the thing that changes are. And that's the lead and the chlorine go from ions to a solid structure, and then that's why it's included. Perfect. That's exactly what happens. If we were to put KCl and lead nitrate in water, we would see a yellow precipitate, a bright yellow precipitate come out, and that is this. Could we see the ions that are just floating around? No. So it's the only visible change that's going to be there for us. Okay? So in a few days, once you relearn this and appreciate what it's all about, I'm going to teach you how to go from step A straight to that. But you need to have this fresh in your head before you'll be able to even do that. Okay? All right, let's do another one. I'm going to change color. Well, if I change color, I wonder if it's going to mess up my font. Yeah, it does. That's dumb. Smartboard is not always smart. Okay, silver nitrate and magnesium bromide. What's the formula for silver nitrate? AgNO3, soluble or insoluble? Soluble, nitrates are soluble, and that is aqueous. And we're going to add that to magnesium bromide. Sure, what's its formula? MgBr2, and that is soluble because it is a halogen, right? But is it Hal hugs Aggies pretty badly? No, it's not one of those, so it means it's soluble. We get a double replacement reaction happening, and we get a silver bromide. That is a solid because it's a halogen and it's an Aggie. Okay? And our other salt would be magnesium nitrate, which we know is soluble because all nitrates are soluble. Okay. To balance, we need a 2 on the silver and a 2 on this silver because we need 2 nitrates. And again, if you can't balance the equation, you probably messed up in one of your formulas. Okay? I feel like I'm always blocking you. Okay, I keep trying to walk over there, but being right-handed, I'm always on this side. All right, 2Ag plus aqueous plus, don't forget it's 2 nitrates. You've got to carry over that 2. And you would catch that at the end because if you didn't include it, you might have 2 on the other side. And remember, they have to be the same number. And if they're not, you did something wrong. Plus Mg plus 2 aqueous. Now, how do I do this Br thing? Do I do Br2 negative 2? 2 Br minus, yes. If you do Br2 negative 2, I'm going to lose it on your paper. Because that's like saying Br gas is negative 2 or some crazy stuff. Yeah, no. Br, there's 2 Brs. This thing splits up into a magnesium ion and 2 separate Br minuses. And so Br minus AQ, we got 2 of them. And that's going to give you 2A, 2Ag I leave this one alone. Why? It's solid. This is going to be a white precipitate, I believe. And then we get Mg plus 2 aqueous plus 2 nitrates that are aqueous. Okay, what do we cancel? Good. Magnesium, magnesium, the 2 nitrates, go. And so our final net ionic species is going to be 2Ag plus aqueous plus 2Br minus aqueous makes. Now, there's something we can do here. This is a little annoying. Balancing-wise, do you see what we could do to still have a balanced equation? Let's reduce it. That's really, I mean, this came out this way because we were trying. Did we? No, I needed to put the 2's in, right? Yeah. Okay. Yeah, so we could really, at the end of the day, this would be acceptable too. It actually bothers me that there's a bunch of 2's in front of it. So there we have it. How are you feeling? Okay, so I'm going to try this on video. I'm a little nervous because I'll be doing the talking. We were told in in-service that we needed to kiss our students on the forehead and tell them to be brave. So I want someone to be brave and go up. I'm not going to kiss you on the forehead. And go up and do writing and take charge, and I will make sure people talk you through it. So who's going to volunteer? I'm tired of writing all the time. All right. So when you're writing, keep your hand at the very far end of the pen. Don't touch your hand to the smartboard. That's perfect. Yes. All right. Rui is volunteering. So we have sodium chloride. What are you going to do to help him there? NaCl. Is that aqueous or not? Aqueous. All right, what is that one? Why is it aqueous? It's Big Daddy at group 1. All right, so we're going to then have 2 products, one of them being lithium chloride, and that is aqueous because all right, and the next one? Perfect. Okay, help him balance. Yeah, what's solid? Is it? Sodium's group 1. Uh-oh, so what do we notice about this? They are all aqueous. Huh. What does that mean? Nothing's going to come of it. So nothing come of it means no reaction, and that's what you're going to write on your paper. Now, in pre-AP, I would have been, okay, and I actually did this. We split it all up. No one really said anything, and then we canceled them all out. Do you all understand that if we were to split these all up, every single thing would cancel out? Okay, if that's the case, you don't need to do that. Just kind of do what he did. Circle that they're all aqueous or underline, and then just say no reaction. Because legitimately, thank you, Rui, appreciate it. Legitimately, that is what happens. You put these ions in, and you put these salts in, they all split up into ions, and they just sit there as ions. They don't come back together to make these, because those are soluble as well. So, and that's another thing I don't know if you've noticed. Any Big Daddy rule, any nitrate, any group 1, they're always spectators. Why? Because they're always soluble. They're always in ions, okay? So that there's the connection there. So we're going to do 2 more. Whoops. And these are done the exact same way, but now we're going to look at them as an acid-base neutralization reaction. Still do it the same way. It's still a double replacement reaction, but here's the important thing about it, and I'm going to write a note way down here at the bottom so it doesn't get in the way. If you have a strong acid or base, They dissolve in water, and they dissociate, so we write aqueous, right? And then in the second step, we split them up, just like any other thing that has aqueous in them. Split them up into ions. This is the only thing that makes weak acids and bases different. If you have a weak acid and base, you also write aqueous. Does anyone remember, though? You leave them. Well, yeah, you could potentially have a double arrow, and we'll get to that. But if you add it to something strong, there isn't a double arrow. It'd have to be both weak. Chloe, what did you say back there? Oh, double arrows. If you were adding them to water, but we're adding an acid and base to each other. So does anyone remember when we had AQ, what we didn't do in the next step, Naira? We don't split them up. So you write AQ, but you do not split them up. What does that mean? That sounds weird. Well, it's telling you that the stuff dissolved in the water, but it doesn't dissociate into ions. So the AQ refers to it dissolving in water. The fact you don't split them up means it stayed together in the dissolved in the water. Okay? So that's the only thing that's going to make these more challenging, which I don't really think is that much more challenging as long as you pay attention. So let's do this first one together. Sodium hydroxide, NaOH, is that a strong acid or base? Strong. According to solubility rules, is it soluble or not? Yes, soluble because, oops, aqueous. It's aqueous because group 1 is a Big Daddy, all right? Is mixed with phosphoric acid, H3PO4. What kind of acid is that? Weak. I want you to make note. If you see a weak acid, make yourself a note because we're going to have to write aqueous next to it, but in our next step, we're not going to split it up. And so when we do double replacement, what do we make? Water and sodium phosphate. What do we make anytime we mix an acid and a base? Salt and water. An acid and a base makes a salt and water every single time. So this water, what do we write next to it? Liquid. And then is sodium phosphate a soluble salt? Yes, so we write AQ next to that. So now we just treat this like everything else, except because this is weak, we're not breaking it up. Do we need to balance? That would help. The beauty about writing water, why did I write it HOH? It helps us in our balancing because we can balance the H and the OH separately. So here I have 3 H's, so I'm going to let that refer to this H, 3. That means I need 3 hydroxides. Oh, I should put a 3 there for 3 hydroxides. 3 sodiums, 1 phosphate, 1 phosphate. Okay, let's do this. 3 Na pluses, aqueous, plus 3 OH minus, aqueous. I split those up because it's a strong base, so it's aqueous. Plus, this is a weak acid, so I leave it together. This is a very high percentage not dissociated when it's dissolved in water. Gives us 3 waters, and I'm just going to put water back the way it was, the way it should be, just because now that I have it balanced. And then 3 sodium pluses, aqueous, plus PO4 minus 3, aqueous. Now, we're not going to have a whole heck of a lot to cancel this time. What can we get rid of? Our sodiums go, and so our final net ionic is 3OH minus aqueous plus H3PO4 aqueous gives us 3 water liquids and a PO4 minus 3. So yeah, it's looking a little like it didn't change much, like a lot changed. There wasn't a lot to just hang out and cancel out. But an acid and a base still makes the salt in the water. This is the base, this is the acid, this is the water, and that is part of the salt. That happens to be a soluble salt. So the sodium was the other part of that salt, which is still there. It's just floating around, not participating. Okay? All right, this last one, I want to change this acetic acid because this is an example of a weak, strong combo. I want to do a strong, strong combo because strong, strong doesn't matter what combination of strong acid, strong base I put together. You can pick any strong acid, strong base in the world. We're going to get the same net ionic equation. And that can be some little powerful trick you know when we get to problems. But I want to make this acetic acid something strong. So give me an example, anything you want that's strong. HCl. All right. What's that called? Hydrochloric. Hydrochloric acid is mixed with potassium hydroxide. So if we have a strong, strong, we're going to treat this like normal. If it's got AQ, we're just going to split it up. So HCl is aqueous, and we're going to add it to KOH. Is that aqueous? Sure is. It's a group 1 hydroxide. Everything's plus or minus 1 charge, which is really nice because it means it's going to be balanced. And so what are our products? KCl and water. And it's already balanced, 1 of everything. All right. So let's go ahead and split up what we can. We have H plus aqueous plus Cl minus aqueous plus K plus aqueous plus OH minus aqueous gives us, what do we do with KCl? Split it up, it's aqueous. This is a group 1 salt plus Cl minus aqueous. What about water? It's correct, it stays together because it's a liquid. So what can we cancel out? The chlorine goes and the potassium goes, leaving behind H plus aqueous plus OH minus aqueous gives you water. This is where they get the word, like where the whole idea of neutralization came from. Look what we're doing. What are we just doing here? We're just making water, right? So you can mix any strong acid and any strong base together. Doesn't matter what kind. This is going to be your net ionic. So if you guys are smart enough on a test to recognize that's strong and strong, and that, so I'm just going to write that, I'm okay with that. But you need to recognize that to get there. So a lot of you didn't get to that level of thought last year when we were doing this because you were still so worried about the process and what's aqueous. Now maybe you can kind of step out a little bit, see the bigger picture, and go, oh, strong acid, strong base, man, that's going to be this equation. We're just making water, all right? So feel free to put that as your answer if you recognize it. But be careful, because not all acids and bases are strong, strong combinations, so you got to watch out. Okay, so you have a quiz tomorrow. Your quiz is not covering this. The homeworks are kind of pushed back a night because of the no homework night, so we're basically behind a night in homework. So the good thing about having tonight's homework tonight is that's what the quiz is over. The last 2 nights, like last night and tonight's homework is what your quiz will be about. So be sure to do that homework, check your answers to be ready for tomorrow's quiz, which is over molarity calculations. And that means all sorts of molarity, finding liters, finding moles, finding molarity, talking about electrolytes and strength of electrolytes. Okay? So look at those 3 charts. Remember the 3 little light bulb things we had in the notes? And then dilutions and solution making. So how do you make a solution from a solid? How do you make it from a liquid using a dilution formula? That kind of thing. All right, that is all. You can work on your homework. You have plenty of time to get that homework done.